Okay, YouTube, in this video we're going to focus on an important fact when it comes to complex answers to a polynomial equation. That is to say, if we have some polynomial equation and we get some zeros here that equals this thing here, maybe we set it equal to 0, we'd say if x is ever equal to a plus bi, one thing I can guarantee you, if this is a complex 0 and b doesn't equal 0, you're going to get a minus bi also. And the reason why is because that complex conjugates, remember we say that things that are conjugates are things that are binomials of the form a plus bi and a minus bi. These would be complex conjugates. But where one binomial and the other binomial are almost identical, but their middle signs clash, they are opposites, we say those are conjugates. So we say pairs of complex numbers of the forms a plus bi and a minus bi where b doesn't equal 0 are called complex conjugates. And we said in example 2, notice that the zeros 2i and negative 2i are complex conjugates. This illustrates our next theorem. So essentially what this theorem says is if f is a polynomial function and you have real coefficients, then if a plus bi is one of your imaginary roots or zeros, then a minus bi has to be the other zero. So when this comes into play is when we want to do something like we have listed here for 5 and 6. It says write a polynomial f of least degree that has rational coefficients and a leading coefficient of 1, but also the given zeros. So here's what I want to point out first. We say negative 1 and 4i. If those are zeros, then first things first, we want to make sure that we add negative 4i to this list here. And the only reason I say that is because if positive 4i, that's 0 plus 4i, is on my list, then 0 minus 4i is guaranteed to be another 0 of this function. And also because we have all of these zeros, what this means is we can go write this in a linear factor form. So we'd say that if I have the zeros, then I know what the factors were. It must have been what we got when we said x minus these zeros. So we're going to drop all of these in here. And I notice that I get x minus a negative 1, x minus a positive 4i, and x minus a negative 4i. I just want to clean this up. Basically, we get x plus 1. Yeah, if x equals negative 1 is a 0, then x plus 1 is a factor. And if x equals positive 4i is a 0, then x minus positive 4i is one of our factors. And here we get x plus 4i is one of our factors. So here is the polynomial. We just want to multiply all this back out. But the idea is that we have to have the complex conjugate in here, and we can write this as the product of 3 linear factors in this case. So in terms of what I want to multiply first, I'm going to multiply these first. And the reason why is because they are conjugates, I know I'm going to get a difference of 2 squares. So I'm actually going to write this squared minus this squared, where in the front here we're going to put our x in the back here we'll put our 4i. So now we could have foiled this. We would have gotten the same thing, but I know that I get a difference of squares. So let's simplify this further. We get x squared is just x squared. Negative 4i squared, well, we have to do the exponent first. So 4i times 4i is 16i squared. And so with this i squared, remember that I squared equals negative 1. So what we really have here is x plus 1 times x squared minus 16 times a negative 1, or in other words, x plus 1 times x squared plus 16. So now we're going to FOIL this out. We end up with x cubed plus 16x plus x squared plus 16. And when we write this in standard form, we get x cubed plus x squared plus 16x plus 16. And this is our original polynomial. So we would say that this polynomial had all 3 of these for zeros because we wrote all 3 factors associated with those zeros, and then we multiplied them back out. So let's take a look at this one here. Now this one's a little bit different. We say that the zeros are 3, 1 plus I root 5. We're also going to write 1 minus I root 5. So we've got a little bit of work to do on this one here, but I say I know all my zeros. So the way this is going to look is firstly we need to write out our factors. So we say x minus a positive 3, x minus now in parentheses this, and x minus in parentheses this. So we're going to put in our complex conjugate roots here. We say 1 plus I root 5 and 1 minus I root 5. So I'm going to tell you that the algebra from this comes from the fact that we are multiplying here conjugates. But we're going to need to do a little readjusting first. So when I say readjusting, let's clean this up. This is x minus 3. Here we're going to distribute this negative throughout, and also here throughout. So we have x minus 1 minus I root 5 and x minus 1 plus I root 5. And where we get our conjugates from is right here. We're going to put parentheses now around this part. And so what I want you to see is that we have this x minus 3 times x minus 1 minus I root 5 and x minus 1 plus I root 5. So this, in our difference of squares sense, is like a minus b, a plus b kind of thing. So what we're going to do is we're going to say we get a difference of two squares. I'm going to write this out fairly large. I'm going to say that x minus 1 goes in the first part of this, squared, minus, we're going to write I root 5 squared. So cleaning this up, we've got a little bit of algebra to work out here. We'd say in here I've got x minus 1 times itself. We have to expand that binomial. And here I would say I squared times the square root of 5 squared. Well, the square root of 5 squared is just 5. So I get I squared times the square root of 5, or square root of 5 squared, which is 5. So here we go. We say x minus 3. Now let's go FOIL this out, and we would get this. We would get x squared minus x is minus 2x plus 1. And then this over here would just become a positive 5 because really we have minus a negative 1 times a 5. So all of this together now, we can combine our constant terms. We get x minus 3, x squared minus 2x plus 6. And now we're going to finish off by multiplying these out here. So we're going to get this. We get x times x squared is x cubed. X times negative 2x is negative 2x squared. And x times 6 is 6x. Now with our negative 3, we get negative 3x squared. Negative 3 times negative 2 is positive 6. And we have an x. And then we say negative 3 times a positive 6 is negative 18. So combining like terms here, we get x cubed. Whoops. Those two together there, we get negative 5x squared. These two together, we get plus 12x's minus 18. So here is our function having these zeros. But we knew that this zero had to exist as a complex conjugate of this zero the moment that they told us that a complex zero existed. Cheers.